When we need to model steady-state, two-dimensional physical phenomena, like ideal fluid flow through a channel or heat conducting across a metal plate, we rely on specific mathematical models to describe the environment. This behavior is captured by the 2D Laplace equation. As shown here against a continuous thermal gradient, it is a second-order partial differential equation that models how potential distributes across a continuous space. But dealing with a continuous space presents a direct mechanical problem for numerical solvers. Computers operate on discrete logic. They cannot calculate an equation over the infinite number of points found in a smooth domain. To compute a solution, we have to transform that continuous mathematical plane into a finite set of distinct algebraic equations. Finite element analysis provides the bridge for this, discretizing smooth geometry into computable matrices. We start by looking at a continuous two-dimensional domain and breaking it down into a grid. For this derivation, we will isolate and analyze the physics of one standard 2D rectangular finite element. To adapt our differential equation to fit this specific rectangle, we apply two sequential mathematical operations, the Galerkin method, followed by integration by parts. The Galerkin method provides a way to propose an approximate solution and capture its error, while integration by parts reduces the derivative constraints demanded by the original calculus. Executing these two steps in sequence is what translates an abstract differential equation into a rigid, solvable matrix. Looking at the primary source text, we begin the derivation by proposing an approximation for the unknown function within our single rectangular element. In this proposed equation, the n terms represent the known shape functions of our rectangle, while the phi vector represents the specific unknown nodal values we are trying to solve for. We take this proposed approximation and substitute it directly back into the original second-order Laplace PDE. Because our proposed solution is an approximation, the equation no longer perfectly equals zero. Instead, the right side produces r, a residual error function. To apply the Galerkin method, we take that resulting residual error and multiply it by our known weight functions. We then integrate this product over the element's entire width a and height b. By forcing the result of this total integral to equal zero, we mathematically minimize the overall error across the element. This initial formulation successfully binds the error. However, it relies entirely on evaluating second-order derivatives on the shape functions, a significant computational constraint for a solver. Here, in the resulting integral, you can see those specific second derivative terms, designated as nxx and nyy. In finite element formulation, second-order derivatives demand higher-order mathematical continuity between adjacent elements, which increases the complexity for a computer to process. To resolve this, we apply our second mathematical tool, integration by parts, relying specifically on Green's first identity for two-dimensional space. This operation mechanically alters the integral, splitting the single equation into two distinct parts. Notice how the derivative terms inside the new left-hand side integral have dropped in rank. The second-order variables are gone, replaced entirely by first-order derivatives. But the operation also produces a critical secondary effect. It generates an entirely new term on the right side of the equal sign, an integral evaluated over gamma, representing the element's outer boundary. By forcing this split, the derivation simultaneously lowers the computational difficulty for the internal area while isolating the specific physics happening at the outer edges. We can now evaluate these two new pieces separately, starting with the left-hand side. Because the domain integral now depends strictly on first-order derivatives of known shape functions, we can evaluate it completely using standard calculus. Carrying out full integration over the physical dimensions a and b yields this specific result: the explicit 4x4 matrix scaled by a fractional multiplier. Looking closely at this evaluated matrix, you can see it is populated entirely by a squared and b squared terms. Every cell inside this matrix is dictated by the physical internal geometry of the rectangular element, and it is multiplied precisely by the column vector containing our four unknown nodal potentials. This evaluated 4x4 grid is the element stiffness matrix. It defines the intrinsic internal resistance, or flow capacity, of the rectangular geometry itself. Next, we shift to the right-hand side of our split equation, the newly generated gamma boundary integral. Physically, this integral multiplies the gradient of the function by a vector pointing normally outward from the element boundary. This mathematical product defines the physical inward flux. We represent this inward flux, whether it's thermal energy entering the element or fluid flowing across a border, using the variable q. As illustrated here, integrating over the boundary gamma for a 2D rectangle means tracing the perimeter across 4 distinct line segments, moving strictly from node to node. Returning to the math, that single gamma integral decomposes into 4 separate edge integrals, isolating the specific q flux crossing each boundary segment. Evaluating these edge integrals gives us a series of column vectors, scaled by exactly half their edge length. These 4 calculation outputs translate continuous physical loads applied along the edges directly into discrete numerical values assigned to the 4 corner nodes. With both halves of the integration evaluated, we can recombine them into a single mathematical statement. On the left side, we have our 4x4 stiffness matrix, mapping the element's geometric resistance to the unknown nodal potentials. On the right side, we have the corresponding load vectors representing the external boundary flex conditions. When set equal to one another, this combination forms the fully realized finite element matrix equation for a single 2-dimensional rectangle. We've taken a continuous partial differential equation and converted it into a discrete linear algebra format that a computer processor can easily read and solve. However, this rigorous mathematical sequence represents the isolated physics of just one finite element. In a functional simulation, the solver takes thousands of these localized 4x4 matrices and aligns them, overlapping the data to assemble one large, sparse, global matrix. Because adjacent elements share corner nodes, their matrices link together. This network allows external loads to transfer flux and potential across the entire geometric domain. Generating these reliable, programmable building blocks was the primary objective of the derivation. Deploying the Galerkin method to capture error and integration by parts to remove heavy derivative constraints, engineers can harness discrete mathematics to accurately simulate complex, continuous physics.